At this point, you already know about 802.11 and you already know about some of these protocols, 802.11b, G, A, and etc. But what you're left to learn is how they came to be together. So the original 802.11 protocol that was designed in 1997 allows for FHSS and DSSS and also infrared and allows speeds for up to 2 megabits per second. So we saw together the DSSS part of it. We mentioned FHSS, but we didn't say it was 802.11, but because it came out of fashion in the later amendments of the protocol. Infrared also was here for historical reasons, because in the 1990s, there were some companies already using the ISM band in 2.4 gigahertz and already doing what was to become what we call today Wi-Fi, but there was no common way of doing things and there was no common protocol to do it. So 802.11 was published in 1997 to try to put things together in a common way. So infrared was there, but it came out of the protocol later on. FHSS was there, it's still there, but it's unused. And the DSSS was there, and this one is still used today. So you have in the DSSS fashion BPSK, QPSK that we saw together. 2 megabits per second is nice, but even in 97, that is not very fast. Already at that time, you have 10 megabits per second on the wired side and people working on 100 megabits per second. So right from the beginning, the 802.11 standard was nice to put things together, to have a common way of doing things, but it was already clear to everybody that the speed we were getting there was just not enough. So as soon as the real standard was published, a working group started working on some new ways of enhancing the speed. At that time, the only way to encode bits into the wave was to use the Barker 11 protocol. But you realize that this is not very efficient because for every bit you send, you have in fact to send 11 bits with Barker 11. So in 1999, the amendment 802.11b was published to increase the speed in this 2.4 gigahertz band and go all the way up to an amazing 11 megabits per second. We're still only in 2.4 here, right? We're not in 5 gigahertz yet. So we still have FHSS, we have DSSS. FHSS is kind of limited because you can only do 1 megabit per second with this part of 802.11. Infrared is still mentioned, but it's something that is away from the main focus of the protocol. So we focus here on DSSS using this wide wave, and with a new technique that is CCK, we can go all the way up to 11 megabit per second. At that time, and actually it started a few years before, some vendors get together and create what is called WECA, which is Wireless Ethernet Compatibility Alliance. And they published the first common part of the 802.11 certification that certifies that these vendors together use the same bits of 802.11, not all of it, but some parts together, and they are compatible with one another. And they name this certification Wi-Fi. So when you have a device that is Wi-Fi certified, it is actually certified originally to be doing 802.11 and 802.11b in 2.4 gigahertz and with a speed of up to 11 megabits per second. As a side note, WECA in 2002 was renamed Wi-Fi Alliance. So what you know today, Wi-Fi Alliance, was originally called another name. So here you are, you have this Wi-Fi certified stamp on your devices for the first time. And the speed you get with CCK are all the way up to 11 megabits per second. But then, of course, the question you'll always get, say, how far do I get? What is the size of my cell if I use 802.11 or 802.11b? And of course, the right answer is, it depends. It depends on so many things. You remember the first module, it depends on the reflection, it depends on multipath, it depends also on the power you put in your access point. So it's kind of a very difficult question to answer. But in those days, the expectation was that the access point would be talking to a laptop. There was no BYOD concept yet. So the physical characteristics of the access points and the clients would be kind of similar. So in the early days of 802.11, they were trying to answer this question with numbers that you could verify in open space. So of course, as you move away from the access point, what happens is that the complex modulation you're using, CCK for example, doesn't work anymore because there are too many losses, too many reflections. The SNR is too low, the RSSI is too low for you to still be able to use that CCK. So at some point in space, very precise point in space that depend on your client is going to decide to revert back from a complex modulation to a more simple modulation. The access point on each side makes exactly the same decision. At some point, based on the signal from the client, the access point is going to decide to use BPSK, QPSK, or CCK, purely depending on its own perception of your signal. So that means, of course, that the AP uses a different modulation for each and every single frame it sends to each and every single client. And the same goes for the client to the access point. So if you have your AP here and you're close to the AP, maybe you can reach that 11 megabit per second. But there will be a point in space where you'll reach and your client is going to decide to revert back to this simpler way of doing CCK with 4 bits instead of 8, and then you'll go back to 5 megabit per second. And then as you move away, you'll go down to 2 and 1 megabit per second. We represent circles, and that's a very common way of representing those areas in the cell. But keep in mind two things. First of all, they are not circles. It depends very much on the space. So there may be some spaces, some directions where you reach farther with one speed than some other directions. So it's more like a potato type of shape than a circle. Also, each client has its own circle. In your space here, you may be getting 11 megabit per second, where my laptop next to yours may only be getting 5.5 megabit per second. It depends entirely on the hardware, my chipset versus yours, my vendor versus yours, my perception of the signal versus yours. But, for simplification, we show these simple circles. Also, the other question is, what power do you use? Because that is going to drive the size of that circle. So it depends on the power, it depends also on the antenna, on its gain, and how the signal is being spread, if it's a sphere or if it's something very flat. So the 802.11 does not mandate a specific power level, but each regulatory domain does. So in the US, for example, the FCC drives that kind of power level. You have the right to go all the way up to 20 dBm for DSSS, that's 100 milliwatt. So assuming that kind of power, the type of distance you would get, assuming that the clients and the AP specs would be almost the same, was about those type of distances. Those were the distances advertised or published as average measurements by most vendors in those days. Do not take those as being absolute values. There is absolutely no guarantee that you'll be able to reach 450 feet at 1 megabit per second. It depends entirely on your client, it depends on the environment, it depends on the access point, it depends on many things. But those were common numbers given as a sort of reference, given a standard access point with a standard rubber duck antenna and a standard client like a laptop.